Hello everyone. As we are continuing our lecture series on vector analysis, in the previous video we discussed divergence and curl of a vector function mathematically. And now in this video we'll discuss line integral of a vector field. Before understanding the physical meaning of divergence and curl, we have to understand it mathematically properly. Most of the times whenever we calculate divergence and curl of any function, then we have to use integration. Why? Because as you know, whether we talk of scalar field or vector field, they are spread over some region. And it is very difficult to find the value of that particular vector field over entire region accurately. Because it can be spread in any form, in any curve. And it is very difficult to apply all the mathematical formula. Somewhere it's straight, somewhere it could be a curve, somewhere it could be parabola shape. So at every point we have to use another formula to find a particular value. But if we know how to use integration, we can ease our job. There are three kinds of integrals that we use in vector analysis, especially in physics whenever we deal with integration. So there is line integral of a vector, surface integral of a vector, and volume integral of both scalars and vectors. After all, we live in three-dimensional world, so either we can find or face something which is line-like, which is just a path, a curve with negligible thickness. So we can consider it to be one-dimensional. In that case, line integral would be of help. But always remember that line integral is found of a vector. Then we can find surfaces also. As we deal with 2D objects, we have screens, we have blackboards, we have tables, desks. We deal with surfaces a lot. So if a vector field is there and we can assume any surface over there, if it encloses some surface, then we can find surface integral. But again, it has to be of a vector. And if we are talking of some object, if it's a sphere or is it a cuboid or something, if it's enclosing some volume, then we can find volume integral. But in that case, the quantity can be scalar as well as a vector. Just the way we remember that gradient is always of a scalar field, and divergence and curl are always formed of a vector function. Similarly, we have to remember these three rules as well. Now, as you can see here in the figure, we have this coordinate system, x, y, and z axis, and this curve you can see. Now, this is just a simple line being drawn. And one more thing is that whenever we talk of line integral, it doesn't mean that it has to be a straight line. Usually whenever we talk of a line or draw a line, we always make straight lines. But here line integral simply means that it is a path, it is one-dimensional thing. Anything, any path, any curve, any line, if it's one-dimensional, if it's not enclosing any surface or volume, we can consider it to be a line, and then we'll find line integral over it. Here we have this A, which is a vector field, and it is depending on x, y, and z. So obviously these are the independent variable. Whenever there will be change in x, y, and z, value of vector function A would change. And it is spread over this region, and we can consider some path. So this, or before that, we can consider 2 points. So since this vector field is spread over this region, we can consider any 2 random points and let A and B be those 2 points. And then we can join them with a curve C. Okay, so this black curve we have drawn. So this is curve C, which is joining points A and B. Now if we have to find value over this entire path, okay, if we say that there is a vector function spread over some region, but we want to know how is it working over this particular region only. We are not concerned with all the space. We are only concerned with a particular region, and that region is this line which has been drawn, or the curve which has been drawn. So we want to know what is the value over here, what is the value over this path AB of A. How to do that now? We will use line integration. And again, as I'm saying, integration, so what does integration actually do? We pick a small segment, a very, very small segment out of the path. We solve it and then we simply integrate it over the entire region. So here we are going to pick this path which has been shown by blue arrow, this very small path PQ, and then we will integrate it over the entire region. So our lower limit would be A and our upper limit would be B. So let's see how we'll do that. So we can write the line integral of vector field A from A to B along the curve C as this way. So here we are taking dot product of A and dr. Why is it important? Because A is spread over the region. Okay, so A would definitely be there. Then the next thing is we need dr. What is dr? It actually tells us that x, y and z are changing. So it gives us the change in x, which is dx, small change in y, which is dy, and small change in z, which is dz. And then the combined effect is dr. And of course, since A is depending on x, y and z, so instead of showing dx, dy, dz all the time, we just use dr. We are taking dot product because we are concerned with the value. You know, dot product of two vectors always give us a scalar, a numerical value. And we are concerned with that only. We don't want to find another vector. Vector field is already spread over here. So if just by solving our answer again comes out to be a vector, then it doesn't make any sense. We already have a vector, but we want to find the numerical value. What is the exact magnitude? What is the quantity? What is the number which is over this region? So that's why we are taking dot product. And then obviously, since it is involving just a line, so dr is there. Okay. If there had been surface, it would have been an area. We would have taken dot product with area vector. If there was some volume enclosed, then we would have taken dot product with volume vector. But now this is a line vector, you can say. Since we are doing our measurement over the line, so we will take dot product with some line vector. And this dr is a line vector, it's a position vector. R is a position vector, similarly dr is also a position vector. Okay, so we can mention it here. So even if something represents change in position vector, but still its nature is going to be a position vector. So it is a line vector. And we have taken dot product because we are concerned with the numerical value, because whatever value we'll obtain, of course there would be some variable because it is depending on x, y and z. So some sort of x, y, z would be there, and then we would substitute the limits a to b to get a final answer. One more thing is that we had this vector field A over this region and we considered any two random points A and B, and we are now trying to find what would be the line integral over the path or over the curve which join these 2 points. But in reality there can be infinite number of paths possible between these 2 points. See, we can draw the path like this also, we can draw the path like this also, we can draw the path like this. So we can draw any number of paths between these 2 points and we can find line integral of all these paths. And it is not necessary that the line integral would be same along all those paths. No, vector field is spread over the region, but you can see at every path, if you consider this particular path, then x, y, z are different. For this particular path, x, y, z are different. So it is not necessary that line integral would come out to be same. So that means when we take line integral, then it depends not only on point A and B, but it also depends on the curve along which we are carrying out our integration. The statement that I've just said, that this line integral depends not only on points A and B, but also on the curve C along which the integration is being carried out. Do you remember this statement before? Have we ever used it before? Where do we read this particular thing? That this particular thing or the quantity depends not only on the initial and the final point, but also on the path taken. Yes, it is the conservative field. You must have read about this conservative field in your early physics chapters or early classes. So we are going to discuss about conservative field in our next video. Since this line integral is actually giving us the hint of a conservative field, so it is really important to discuss conservative field here. So after finishing this topic of line integral of vector field, in the next video we will discuss conservative field. Now the integral that we have taken, basically we have considered all the vector segments to be dr. See here, this PQ that we took, considered, that is dr, and then we are just integrating dr, all the dr's over A and B. And this dr is a very small vector. It is infinitesimally small. So I need to mention here, see, one word is infinity and another word is infinitesimal. Both are opposite to each other. Infinity means something really extremely large, and infinitesimal means something which is extremely small. So here we consider, whenever we do integration, we consider very small segments, infinitesimal segments. So this is infinitesimal vector displacement along the curve C. And why we are saying this displacement? Because after all, vector A is a vector field. We are talking of a vector field, and dr is also a vector. And of course, in case of vectors, we have displacement. What is the difference between distance and displacement? Distance is a scalar quantity and displacement is a vector quantity, because it has both magnitude and direction. And since here this vector field A is a vector quantity, so we have to consider all the terms which are vector quantities to actually understand it. And that's why we have considered dr to be displacement and not the distance. Distance is meaningless, because then we cannot take the dot product between a vector and a scalar. That is just not possible. Okay, so this is our infinitesimal vector. And now you can see that all these vectors, see, this vector is not only over here, it is over here, it is over here, here, everywhere. So we are just considering at one particular portion, and then we will just integrate it over the entire region. So here, as we've just mentioned, that these vector segments dr, they are all vectors. They are vector displacement. So they must be pointing in some direction, because vector is associated with direction as well. So what is the direction? Direction is from A to B. See, all the vectors are going from A to B. A is our lower limit, B is our upper limit. So whatever is going on, it's because it is a vector quantity, so direction will definitely be there. So we have to see where it is going. So it is going like this, going from A to B. So all the infinitesimal vector displacements dr that we have considered, they are also pointing in direction A to B. See, this vector that we have drawn, the arrow is pointing toward B. Here the arrow is pointing towards B. So all the vector displacements, they would be the vectors which are actually pointing in direction A to B. So here they are all pointing in direction A to B. And then the thing is that if we evaluate the same integral from B to A, now you know if you just swap the limits, your answer changes. Why? Because whenever after solving something, suppose we have this A to B and 1 dot dx, or if just remove this dot here, because now dot represents dot's product. So here I'm just going to write like this. Okay, so this would give me x, and then I have to put the limits. So if I do like this, the answer would be b minus a. But what if I change the limits? I swap them. So if it is b to a dx, then the answer would be a minus b, and both are not equal. Okay, so this is the meaning that the integral sign, this integral would change if we swap the limits. So here if we integrate from b to a, in that case integral changes sign. It just changes sign, as now dr will point in opposite direction, because now vector will start pointing in opposite direction, and direction really matters. So if we are solving any vector quantity and its direction is changing, it means the vector is changing, and that would affect our answer as well. Now let's try to evaluate what the expression would look like. So in Cartesian system, that means we are referring to our 3D coordinate system. We can write down this vector A as ax I cap plus ay j cap plus az k cap. And vector dr can be dx I cap plus dy j cap plus dz k cap. Now this should be remembered by all. How do we represent vector r? How do we represent dr vector? And what is the general expression for any vector? If the vector is in three-dimensional system, if it is depending on x, y and z, then obviously there would be some component along x, some along y and some along z. Now if we have to take a dot dr, because as you know, we just wrote that this line integral is dot product of vector a with dr integrated over limits a and b. So we can write it as, see how important this dot is. This dot product has a lot of meaning. And now we know how to solve dot product. I will only interact with I cap, j with only j, and k cap with only interact with k cap. And now I'm directly going to write the answer. And now you can see that this answer is simply a scalar quantity. Now let's give this equation number 2. This is our equation number 2. Now if we substitute this in our equation 1, see this was our equation 1, a dot dr integral. Now we know what is the value of a dot dr. It is simply a scalar. We have obtained a scalar quantity. But definitely it includes some component of x, some component of y and some components of z. So if that's the case, then we can write this line integral as a to b, and now we can simply substitute for a dot dr, which is ax dx plus ay dy plus az dz. And now we can also put these integral over all these three terms separately. So we can write it as integration of ax dx over the limits a and b plus integration of ay dy over the limits a and b plus integration of az dz over the limits a and b. So this is the way we can write it. This is the final answer. So whenever we find any line integral, this is the answer that we will obtain. All we have to take care about is the limit. Okay, the limit would be substituted in the end, but otherwise it would be the component, the x component of vector with the change in x coordinate, and simple multiplication is there now. And here we will not say even multiplication, it does only means that we are going to integrate ax with respect to x. Okay, so this ax must be containing some x values, and here this simply means that the y component of vector a will be integrated over y, and z component of vector a will be integrated over z, and in the end we will put the limits a and b. So it is as simple as it seems. Now suppose, for example, this vector a is force. Okay, you know we can denote force by this letter with an arrow overhead. So suppose our vector field a is force, and of course it is the force is acting on a particle which is moving along this curve C. See, this particle is moving along curve C, and this force is acting. So we can say that the force is acting on this particle. And now we have to find what would be the overall effect of force over this entire path. Then now we have to take the line integral, because we know we only have some path given to us. Now we know how to find the line integral. It would be simply, the answer would be whatever is the limit, okay, and then x component of force will be integrated over x-axis, or we can say with respect to x. Then whatever is the y component of force, that would be integrated over y, and whatever is the z component of force, that would be integrated over z. Can you tell me what is this quantity? Or in general, we can mention that that would be f dot dr. Do you remember what is this quantity? This is work done by the force. Remember the formula of work done? Work done is often written as f dot ds. We used to write. Sometimes we write dx and then we mention it at f ds cos theta. In the work chapter, work, energy and power chapter, you must have read this. So this can be found simply by using line integral. One another example we can understand is, suppose our vector A is electric field intensity at some point. Then the line integral of this electric field intensity would give us potential difference between those 2 points. If the points are A and B, then we would obtain potential difference. This is again the formula between A and B. So this is another example. We can understand line integral in any of these forms.